Alright, so we're just going to walk through the mechanics of the pendulum. I'm just going to draw out the scenario for you real quick. Here's your pendulum. This is basically when it's at a perpendicular to the to where it's hanging from. Pendulum mass M. You have a string of length L, theta is your angle, and your arc length is S. From geometry, we know that the arc length S equals theta L. Now, if we draw a force diagram for the mass, we have the force of tension, which only acts radially, a radial force of gravity, which should balance it out, your normal force of gravity, and then, or the total force of gravity, and then force of gravity in the tangential direction. Now, we're just going to be focusing on the tangential direction right now. So if you have sigma F in the tangential direction, it is basically negative mg sine theta equals mass times acceleration in the tangential direction. I used a negative because we're just treating the left as the negative side. So if we convert this into a second order derivative, we end up with second derivative of position with respect to time equals negative g sine theta. Now this is the point where we can use what's called the small angle approximation, which is essentially this just turned around. But if we have arc length S is equal to r theta, and this h is equal to r sine theta if theta is here. So what the small angle approximation it says is basically if the angle is equal to or less than 0.1 radians, then we can assume h is about equivalent to s, which would mean sine of theta is about equivalent to theta, and cosine of theta is about equivalent to 1. So bringing this down here, that means we can say that instead of negative g sine theta, it's just negative g theta, and we still know from this that theta equals s over L. Now, if we substitute this back to our force equation, F equals ma, which is also m d squared, second derivative of position, just so you can see it there, equals m g, negative mg theta, and if we substitute in this for theta, we get negative mg s over L. Now how we're going to use that is basically we can solve this this derivative by analogy, because the m goes away once we cancel it out if we set it equal to another force equation. So we're left with second derivative position equals negative g s over L. It might be easier to see it if I draw it like this, because then we know that omega equals the square root of g over L. This is useful because basically it helps us find the rotational velocity and so of a pendulum with a bob, so a string and a bob. To the equations we learned earlier, we have our regular position function for an oscillation, we can also use theta instead of x, and it's the same thing.